now let us, for some technical reason, the slides did not continue after the example of pure coordination. So let us again look at the example of exercise or example 56.3 from Osborne and Rubinstein. So that example, I hope now you can see it. The example has 4 strategies to player 1, A1, A2, A3, and 4. And 4 strategies to player 2, B1, B2, B3, and B4. And we want to find all the rationalizable strategies. So a strictly dominant strategy is never a best response, so it cannot be rationalizable. It can not be used to justify a rationalizable strategy. So we can just delete those and let us start deleting, and then we see what we are left with. But we can delete those without changing the set of rationalizables, without changing rationalizability, because they won't play a role there. So B4 is strictly dominated by 3/5 B1 plus 2/5 B2. So there is a convex combination of other strategies. In other words, a mixed strategy which strictly dominates B4. So we can delete B4, that column, and result in the following matrix. Now, notice that A4 now strictly dominated by the mixed strategy which combines half A2 plus half A3, and therefore A4 can be deleted. So we are left with the following matrix, and here nobody is strictly dominated by any other mixed strategy. It can be checked simply by, actually it's simple to check. So A1 has the highest number in the third column. It cannot be strictly dominated by any combination of 5 and 0. A2 has the highest number in the second column, and N3 has the highest number in the first column. So nobody of those strategies is strictly dominated by any combination of the others. And similarly, B1 has the highest utility in the first row, 7, right, is higher than 5 and 0. B2 has the highest utility in the second row, and B3 has the highest utility in the third row, 7 higher than 5 and 0. So nobody can be deleted based on this idea that it's strictly dominant. Now what can we do? So we claim that actually those are already rationalizable. So we will prove a theorem which says that if we cannot delete anymore, then all those are rationalizable. But by now we don't have this theorem. So we need simply to check concretely why they are all rationalizable. And that's simple. So A1 is in the best response to a strategy which plays strategy 1, B1, this is probability 0, B2 is probability 0, excuse me, and B3 is probability 1. So 0, 0, 1 is the mixed strategy, is the belief, if you want, on the strategies of others, such that A1 is a best response with respect to those, because if you play B3, which is probability 1, A1 gets 7, it gives player 1 7, A2 gives 5, and then 3 gives 0. So definitely A1 is a best response. And so on. So we show that every strategy is a best response with respect to some probability distribution on the others. And therefore, those are those are rationalizable, because we can say that Z1 is A1, A2, and 3, Z2 is B1, B2, B3, and everyone in Z1 is the best response for some distribution on Z2, and everyone in Z2 is the best response to some distribution on Z1. So according to the second definition, A1 and 2 and 3 and B1, B2, B3 are all the rationalizable actions. Are rationalizable, and as we said, the others we've already deleted and they cannot be rationalizable. So okay, let us now talk about something else, so that we allow the beliefs about what others do to allow for dependency. Now, there are definitions, other definitions in the literature, which, similarly to the mixed Nash, assume that the profiles of others are independent. So at every level, when we talk about some belief of what others do, I assume that the belief about the probability of player 1 doing something, player 2 doing something, and so on, everyone besides me, let's say player I, it's simply the product of what is the belief about player 1, what is something about player 2, and so on. So there are definitions who assume that it is independent, and the definitions are not, generally speaking, the same. And now let us just show an example, also from Osborne and Rubinstein, that our definition, when the belief is allowed to be general in particular dependent, is not the same as if the belief had to be independent. So consider the following game. 3 players, 1 chooses a row, 2 choose a column, and 3 choose a table, one of 4 tables. So player 1 has strategies up and down, U and D. Player 2 has left and right, L and R. And player 3 has M1, M2, and 3 and 4. And the players are identical to every player, and they're written in the table. So this is the game. And 3 players, 1 chooses row, 2 chooses column, 3 choose table. Now, here I just have written the columns, the tables, one after another. It's simply to fit them on the slide, but these are different tables. So, according to our definition, M2 as the action of this player 3 to choose matrix 2, this one, is rationalizable, but it's not rationalizable if the beliefs have to assume the independence of the strategies of the others. So, in general, this our definition and the definition which assumes independence of strategies of the others, which we don't work with unless we say these are different. So why is M2 rationalizable in our sense? Because for U, upper is an optimal strategy of player 1 if the others choose low and M2, right? So M2 and low. For player 1, it's better to choose 4 than 0. If others choose, by the way, it's not a formal writing, of course. It's not a distribution. I just write this informally, but I hope you understand. I mean here that the strategy that deterministically chooses R, and the second player chooses R, and the third player chooses M2. So when the second player chooses R and the third player chooses M2, the first player, so this is the option, then D is the only best response. Additionally, if you're talking about the second player, now, and the first player chooses either up or down, and the second player chooses M, so the third player chooses M. So whenever the third player chooses M, I don't know what the column player chooses. But, excuse me, I don't know what the row player chooses, up or down. But I know that the third player chooses M. So then, the best response can also be sometimes L, sometimes R, depending on what the row player, which I don't constrain, chooses. So the set of best responses is all the strategies of the second player, all the strategies of the column player. And if I assume that the column and row choose up or low with probability half, and though down right with probability half, here I use the idea that they have to be coordinated. So I cannot choose up and right. I choose either up or low or down and right. Then M2 is the best response. Please note that it's important that I don't allow miscoordination here. Because if I allow miscoordination, then it can be 0 and then it will not be the best response. So it seems that we may have this distribution. So upper, low, or down and right. These are the only options. Then M2 is the best response. And then the follow threads are rationalizable. According to the second definition, Z1 is up or down, Z2 is low, left and right, and Z3 is M2. Because up or down, each one of them is in the best response. Well, then the strategies of the others, which can be in this, can have a positive probability in the distribution. The distributions which give once U as the best response, another one D. The possible strategies of the others are low or right for the second player, all options, but all this M2 for the third player. They are all in the Z2 and in the Z3. Now, in order to justify L and R of the Z2 of second player, it's enough that we allow anything for the column player, which is indeed Z1, and M2 for the third player, which is Z3. And M2 can be justified by a distribution on upper, lower, down, and right, which are in Z1 and Z2. So according to the second definition, these are rationalizable strategies. And M2 belongs to Z3, so M2 is rationalizable. Now, on the other hand, M2 is not rationalizable if the beliefs have to assume the independence of the strategy of the others. Because M2 is not the best response for any independent distribution of the strategy of the others. Because if it had been the best response for some distribution that P1 minus P for up and down of the row player, and Q1 minus Q for left and right for the column player, then the utility from choosing M2 would be P times Q times 4, this one, plus 1 minus P times 1 minus Q times 4, And this has to be at least the maximum of other utilities have to be in order to be a best response. So for what are the other utilities? So for M1, it would be PQ8. For M2, it would be 1 minus Q8. And for M3, it will be all these 3. And this inequality can be shown to never hold for P and Q between 0 and 1. So M2 is never a best response, and therefore is not rationalizable in our sense. So it does matter that we allow the beliefs to be any beliefs on the others. And now let us go to the iterative elimination of strict determinative strategies, a topic we already discussed once. But now let us go and discuss it a bit deeper and combine it, connect it to the definition of rationalizability.